All right, everybody, thanks for coming in. This is the second to last session of the day. This session's focus is going to be on fully homomorphic encryption and multi-party computation. We're getting into magic crypto territory, and so this should be really fun. Our first speaker is an invited speaker, and so everyone give warm welcomes to Shruti Gorantala. Shruti.
Thanks, Nick, for the intro. Hi, folks. I'm Shruti. I'm part of the FHE team at Google, and I'm here to talk about fully homomorphic encryption, some of our adventures and learnings as we try to bring FHE to production. As the title suggests, the agenda provides a way to navigate the ciphertext space, which is basically programming on encrypted data, which I call the FHE stack. And because FHE is such an interesting and challenging space, I talk about using a more abstract framework called a hierarchy of needs to define a path to real-world FHE that is using FHE for privacy. So what privacy benefits does FHE provide? In the current world, we have secured storage and secure communication, but not secure computation. And FHE bridges this gap. In doing so, it provides many benefits, such as it prevents insider risk. That is, it prevents internal employees from accessing user data. It ensures policy compliance and also data minimization. Give data access to the fewest people and jobs possible. And as you all know, fully homomorphic encryption allows computation on encrypted data. And the concept goes that for every function that you can perform in your plain text space, there is an equivalent function that you can perform on the ciphertext space. And this is made possible by a noisy encryption scheme called the learning with errors encryption scheme. So in this scheme, to encrypt a message, small noise is added to large random samples for protection. These samples are large. The ciphertext here is the sample and the encryption, and the samples are to encrypt 1 bit, you need 720 integers. So that's almost a ciphertext blowup of 20,000 times. There's a variant to this, which is the ring version, where you encrypt vectors of messages, but there's also a ciphertext blowup there. This noise is kind of the boon and also bane of FHE. There's a complicated relationship between noise and message here. As you do computations on your encrypted data, the computations happen on the message, but also the noise accumulates. And it might reach a point where it corrupts the message. And that means that we need to do noise management. We can do this noise management either by choosing large parameters to incorporate your entire computation, or you can track the noise and perform what we call these ciphertext refresh operations periodically. So as you can see, there are many challenges when you start thinking about programming on encrypted data. And they can be categorized into the first one, which is data expansion, which is obvious, the ciphertext blowup. Speed, because now you're performing your computations on this huge ciphertext space. And also, the simple computations such as addition or multiplications or gate operations are not the same as they are on plain text space. They are much more complex. They require noise management. And usability is because of all of these bells and whistles that go around with trying to do manage noise as well as computations. So if you think about FHE programming, it's a bit of a cognitive overload. In traditional cryptography, encryption and decryption can be thought of as serialization, deserialization layer just before you send a message or just after you receive a message. Messages are just bits. You don't think about what computation you perform on those bits when you encrypt them. But FHE, you're hyper aware. The encryption algorithm needs to be hyper aware of the kind of computation that you perform. So there is the plain text universe, and there's the ciphertext universe. And you'd think it's just one universe, but actually it's a multiverse of FHE schemes. Depending upon how you encode these messages and error, there are multiple schemes. In some schemes, are good for gate operations or lookup tables. Some schemes are better to do integer computations, while some schemes are good to do approximate fixed point arithmetic. And okay, so if you put on your developer's hat, you know you have your application, it requires some basic primitives, you pick your scheme. Then there are many libraries that implement these schemes. And each of these libraries expose primitive operations. Now, how are you converting your bigger application to those primitives? Thankfully, there are many libraries. But each of these libraries is, again, optimizing for a specific scheme or a specific type of computation or application. How do you interop between these schemes? And then there are hardware accelerators because FHE is slow. And there are many amazing hardware accelerators. The first question that comes to mind is, do they exist for real? Will they work for my application? So coming to the research in FHE side, a popular fable comes to mind. It's called Blind Man and an Elephant. A bunch of blind men come across an elephant, and each of them is trying to describe the elephant by describing the part that's closest to them. Some are describing the trunk, some are describing the legs, some are describing the tail. But the bigger picture is missing. FHE research is kind of in a similar state. There are many optimizations, many schemes, and all of them are important and all of them are needed, but a bigger picture is missing. And here we propose this FHE stack where we try to put it all together. On the top left is what we call FHE architecture selection module, which selects your parameters, which selects the schemes for you, which does encoding. How do you encode your message into this ciphertext space? And on the right is, think of this as a compiler toolchain. If you think of FHE as its own computing machine and ciphertext as registers, then computation on these registers will incur some cost, and we need to find a way to optimize for performance while preserving privacy. And this is a lot like the LLVM toolchain. It provides a lot of optimizers and schedulers, and I'll be going down the parts of the stack in a bit, but just to give a sense, it follows the basic compiler architecture. There's a front end, there's a middle end, there's a back end. And some of the principles that we try to follow is modularity. Domain experts can perform their work in their domain without worrying too much about other expertise. Interoperability. Each of the modules need to work well with the rest of the modules. And reusability. So experimenting in one module should not require for other modules to be built from scratch. So we focused on one part of FHE schemes, that is TFHE, that is optimized for gate bootstrapping. Now, bootstrapping is one way of ciphertext refresh operations. It reduces the noise so you can continue to do unlimited set of operations. So we assume there's human input in the FHE architecture selection module, so we choose a standard 128-bit security parameters. We choose binary encoding and gate bootstrapping. So let's begin with a plain text program. This is a basic string capitalization program that capitalizes the first letter of every word in a string. There's two interesting things here. One is there is an if-else condition, and the second one is there's a for loop. So this comes to the first part of programming in FHE. It's a data-independent programming paradigm. It's known, but as you actually start programming, do you realize that there needs to be a lot of changes that need to be made to your program? So if-else condition needs to be rewritten as a multiplexer because the server does not know when to branch. So you would have to execute all the branches, and the condition would pick one branch selectively. By the same logic, how will the server know when to end the loop if it doesn't know what the loop variable is? So loops need to have static upper bounds. And there's no branch and bound optimizations. So every graph is like a fully connected graph. And turns out all of these problems are handled in high-level synthesis, which was hardware synthesis, which converts high-level programs to a representation that can be executed on hardware. So we convert that plaintext program using a high-level synthesis into a circuit. And the power of this intermediate representation of a circuit is that if you write your parser of any high-level language and convert it into the parser, into this intermediate representation, you can execute the rest of the stack. And this becomes obvious here. The FHE optimizer converts that initial computational circuit into a circuit that you can execute with FHE. In this, because of these intermediate representations, it was very easy to integrate this with state-of-the-art Yosis ABC optimizations. And we found that it almost always reduces the circuit size by 40 to 50%. So there's a really good speed up there. And as you can see here, the computational graph is a directed acyclic graph. Now, executing this graph just means going through this graph and then rewriting some of these nodes as gate nodes that perform on ciphertext. So that comes to the next part of the stack, which is the execution engine or the transpiler code gen. And the transpiler code gen does two things. We call it a transpiler and not a compiler because it emits code, it emits a library. And that's powerful in its own way because then it is not dependent on the language in which the library is written. So your library could be in Go or C++ or Rust. The code gen can just emit code. So the transpiler code gen emits a scheduler to run these operations on the server side. And it also emits code that helps you to encrypt and decrypt on the client side. So ignoring the things on the top, which is what the server-side scheduler is being emitted, the bottom box shows that you can now define your complicated data structures and then just say the data structure dot encrypt. It would do all of the bookkeeping for you. So coming back to the scheduler. So the execution engine emitted schedulers. What I showed before was a simple scheduler. It just emits code. And the simple single-threaded scheduler doesn't take advantage of parallelism. So in the circuit scheduler stage of the stack, you can define your schedulers that are actually more suited to the hardware that you're using. So having a multi-threaded scheduler on a multi-core CPU performs great for CPU, but it might not perform as well for GPU because GPU performs on a data parallel scheduling. For GPU, you need all nodes of same type to be executed at the same time. So you could define your SIMD scheduler, single instruction, multiple data scheduler for GPU. You could define single program multiple data scheduler for TPU. Now, FHE programs are huge. You might need to be distributing them across a fleet of devices, and at which point you might need a distributed scheduler. This is kind of my favorite part of the FHE stack because it's a very interesting interplay between trying to optimize between distributed systems and computer architecture. So now we have a scheduler. All the scheduler is doing is making calls to the FHE library, which is the core crypto implementation. The core crypto implementation at this point is an API that exposes data manipulation instructions, which are the instructions that you perform on your plain text. It also does ciphertext maintenance operations, which is doing this noise management. And then there's some specifications for support. So that's all the FHE library part is doing. And then comes the more interesting part, which I call the micro instruction scheduler. This is the interplay between the FHE library and the physical hardware optimizations that you do. Now, these physical hardware optimizations could be going one layer below the crypto system into the math layer, where in all of FHE, the baseline operation is polynomial multiplication. So if you can accelerate your polynomial multiplication in the hardware, it has massive speed up. You can go a level above and actually accelerate these crypto primitives. So the interesting thing in the hardware world is you measure these crypto primitives based on throughput. So assume 100% parallelism. But programs are not 100% parallelizable. How do you translate these amortized primitive speedups to end-to-end programs? And that's where FHE stack comes into play. It applies the basic principle of computer science to FHE. Control the complexity with layers of abstraction and make independent progress. And it allows for experimenting with variety of optimizers and crypto systems and hardware without having to rebuild other components of the stack from scratch. So we were able to integrate multiple optimizers, as can be seen in the layer there, and multiple schedulers, single-threaded, multi-threaded, GPU, and multiple crypto systems. Now, all of these crypto systems support gate bootstrapping. There's TFHE that we began with. There's BinFHE from OpenFHE, TFHE Rust from Zama Concrete, and there's cuFHE. And some of these libraries are integrated with some of these hardware, CPUs, GPUs, FPGA, and believe it or not, photonics. There's a company called Optalysis, which is doing photonics for FHE. And this is what the FHE stack unlocks. End-to-end metrics. This is more of a toy problem, but it illustrates the power of having FHE stack. And all right, so what I'm trying to show here is there is bootstrap, which is 13 milliseconds for CGGI TFHE scheme. And the circuit size for this was 920 gates. In a single-threaded model, this took 53 seconds. And when you do it a multi-threaded on a 96-core machine, there's already an order of magnitude speed up here. It reduced down to 1.84 seconds. And using Yosys optimization, the circuit size reduced to half. And the speed is now less than a second. And it translates to one of the DM schemes in BinFHE as well. The single-threaded is much slower, the multi-threaded is much faster, and with Yosys, the speed translates. Now, there are many new crypto libraries where the bootstrap has been accelerated. In TFHE-RS, the bootstrap speed is 12.5 seconds. And there may be other optimizers. There's the concept of lookup table that a concrete library introduces, and it would be interesting to see how scheduling that would actually increase the speed up. Same goes for GPU and FPGA. There is 2 orders of magnitude speed up in Bootstrap with FPGAs. And we are in the process of figuring out the results of these end-to-end metrics. So, oops. All right. So there is the Boolean world, and now to unpack this thing that we assumed has human input. In the domain-specific programming for FHE architecture selection, there needs to be a lot more parameter optimization for arithmetic. And we think that multiple passes between the FHE optimizer and the architecture selection module would help with integrating these new optimizers for arithmetic circuits. And a lot of changes need to happen in the arithmetic scheduler as well. So this kind of puts together the whole computing on encrypted data model. So are we having FHE yet? Not quite. I didn't talk about key management. I didn't talk about trust model. In theory, computing on encrypted data kind of gives you privacy, but in practice, not really. So to talk about how these things fit together, I'm going to use a popular framework in psychology called the Maslow's hierarchy of needs. Maslow's hierarchy of needs is a term in psychology that talks about stages of growth in humans. For motivation to arise at a next stage, each prior stage must be fully satisfied. And the hierarchy of needs is split between deficiency needs and growth needs. Deficiency needs are for survival. Growth needs are for humans to realize their true potential. So this is the FHE hierarchy of needs. On the very bottom is level 1 is baseline instruction set architecture. We need to have, if you think of FHE as a computing machine, having the basic instruction architecture, which could be both data manipulation or ciphertext expansion, and hardware cost. And the primitive instruction set and its cost is important, and only then can you think about developing compilers and transpilers. And once you develop compilers, only then can you think about putting an FHE application together. Only after it becomes easy to develop programs on encrypted data do we think about actually deploying FHE for privacy. And only after the system and privacy engineering problems are solved do we see FHE realizing its true potential in privacy. So deficiency needs, the bottom three are the deficiency needs. And a hierarchy is a more abstract term. On the bottommost layer, it talks about the needs. So the bottommost one, the instruction set architecture, the needs are instructions and the cost. In the second layer, we worry about parameter selection. We worry about optimizers, cost models, schedulers, intermediate representations. On layer 3 is where we think about development speed, debuggability, scheme interoperability. Even though scheme interoperability came in level 3, actually it's addressed by ciphertext maintenance operation in level 1. It's a more abstract framework. So we think FHE stack addresses a lot of these deficiency needs. We hope that FHE stack can evolve into something that addresses these deficiency needs. So the success here in the deficiency needs is, I love cryptographers, but I do think cryptographers are the bottleneck in the deficiency needs. The success here lies in empowering the users to be able to develop their own programs in encrypted data and make these trade-offs themselves. But the cryptographer is heavily, heavily needed in layer 4, where you do actual protocol development for privacy. And here is where threat model, privacy leaks, network bandwidth, and something that we don't think about, observability. As you think about deploying a large-scale application, end-to-end encrypted, how would you log any metrics? How would you know if something goes wrong in a large-scale system? So layer 4, firstly, key management. If it's one user with a server, then it's a single key. If it's an email setting, there's a public-private key setting. If there's a multi-party computation, there might be a multi-key setting that's needed. And as we have seen, end-to-end encryption with cloud storage is really hard with key management and backing up keys. Secondly, the trust model and protocol development. FHE is but a puzzle piece in the set of privacy-enhancing technologies. So far, I have assumed that there is an honest but curious model. What if the server is adversarial? You might need zero-knowledge proofs. What if the client is adversarial and trying to learn something about the model? You might need differential privacy. And it's very interesting how you can leak data size to the server. It's kind of understood in traditional cryptography, but it has a more adverse effect on performance in the FHE space. So if I'm trying to do translation, how long is my output string? If it's always 500 characters or 1,000 characters or 1,000 words, then you're always generating 1,000 words, which is bad for performance. So you may need some form of probabilistic sizing, so you still hide the data size, but also get the performance. And the open problem, ciphertext expansion. There is packing and hybrid homomorphic encryption, which might help with a ciphertext expansion, but it's not a full solved problem yet. Okay, so on the top of the pyramid is FHE actualization. What does it mean? In a large company, at the beginning of quarter, at the beginning of the year, the team comes together and they think about the product having some latency tolerance, some network bandwidth tolerance, some privacy requirements, some budget for hardware, and product timelines. And as we talk to a lot of products, there are many latency tolerant applications available out there. But the issue right now is the time required to develop FHE. And if it takes a few years to launch a product teams tend to look for alternative options, less private options, probably not what we want. While speed up numbers for primitives are great, what would be more useful is these end-to-end benchmarks with end-to-end application perspective. So we are somewhat at level 3. As you can see, FHE is now an interdisciplinary field between theoretical cryptography, compilers, hardware optimizations. I hope the FHE hierarchy of needs and the stack serves as a framework to organize research and accelerate FHE parallelly. And as Pascal pointed out a few days ago, FHE is like where deep learning was 10 years ago, reaching the realms of reality, but lacks a lot of tools. And developing those seamless tools and empowering the developer is what we need. And that's our repo where we are working towards bringing FHE to practicality. And if you have thoughts, questions, we have a discussion group, and please reach out. That's our group email, and that's my email as well. Thank you for listening.
All right, thank you. Yeah, that's amazing. It's like we're reinventing the computer inside of a cryptographic computer. So, folks, if there are any questions, I'm going to take some questions from online, but please come up and come to the front of the stage. Don't be afraid. And in the meantime, the folks in the back, there's a lot of seats up front if you want to come up and take a seat. So, please.
Thank you so much for, like, I don't know, the way you organize this information, it makes it feel like we have a goal with FHE. And it's just really cool to see it like presented this way. I don't know this field very well, but I'm curious if you have any thoughts on like the momentum of theory in the field and how this like impacts you at lower layers. So if the math is changing constantly underneath you, how does that impact like higher level considerations? Do you plan to like keep some agile like in your stack, or are you just going to pick some math and go with that for a while? Like, what's your thinking?
That's a great question. So yes, we want to keep the stack agile. Hopefully the FHE library and the lower layers lower it will kind of take care of like even if math changes. But to be honest, the theory has not changed for years now. The Ford schemes still remain the same since years, and it's more of compiler optimizations and hardware optimizations that are needed at this point in time.
Cool, thanks.
Thank you for the question.
Yeah, so I guess on that note, one of the things that can change is also the security model or the correctness model, the underlying scheme. And right now I'm thinking about approximate FHE schemes. And I'm curious what role you think, in general, approximate computation plays in this stack, and more open-endedly, future alternative notions of correctness.
That's a good question. So I guess just to place it in the head, in the FHE schemes, there are integer schemes and floating point schemes. For floating point schemes, you would have to do approximations. For integer schemes, even for machine learning models, you might have to do some form of quantization. So there is always this tension between performance, precision, and privacy in FHE. How do I think about this? There's no alternative, first of all, for approximation. So if you want better precision, it's a trade-off that a product needs to make at this point in time. In machine learning world, the alternative is you'd retrain your model, and this also is needed. But at the same time, there are machine learning scientists spend a lot of time trying to train their model, and asking them to retrain it is like, no, I'm not going to do it. So we might still that's a trade-off that products need to make. Maybe there we will reach a point where data becomes that so sensitive that retraining is okay, but yeah, only time will tell, I guess.
Thanks.
Okay, we have time for one last quick question.
So currently, like zero knowledge proof systems, MPC, and then FHE are all developing kind of similar systems like this. Basically, you get IRs, optimizers, compilers, execution layers along entirely different tracks. So they're not combined at all. I guess I'm curious: is there any opportunity to combine this infrastructure, like cross IRs that work across MPC and FHE and ZKPs, or maybe like math layers, et cetera, et cetera? Is there any opportunity for that?
I'm pretty sure there will be. I don't know what they are right now, but they are somewhat different. I guess SMPC kind of, you keep sending these one-time pads to do your computation across. It's more about communication. But if you see the FHE stack, a lot of the layers are unaware of crypto. So maybe we can develop these intermediate representations with our cost models and our operations such that you can still reuse these optimizers across. That would be a very interesting crossover to see. Thank you.
All right, everyone, please thanks Shruti again.
Thank you.
All right. The next speaker is, and I'm going to butcher this, I'm sorry, Antigone Polychroniadou. Is that anywhere close to right? Okay, thank you. This next talk is going to be on a project called Prime Match. So please thank the speaker, Antigone.
Thank you. Okay, I have to stay closer. So I'm going to talk about Prime Match, which is essentially a privacy-preserving auction system, which is running live in production at JP Morgan. And Prime Match started as an ambitious project because it's the first bank that runs such a service, and it's the result of 3 years of active work to put successfully in production. And in this talk, I'm going to talk first about the use case, and then our contributions. And since we're in real-world crypto, I'm going to focus more on the production challenges to put such a real-world system in production. I will only have time to talk superficially about our cryptographic solutions. Our techniques deserve another talk. And at the end, I'm going to actually show you a demo. So what is the use case? The use case is inventory matching. And inventory matching is used by banks to actually locate matches between buyers and sellers. And if successful, then the banks can offer these trades at discounted rates, avoiding additional costs and price volatility if you were to execute those trades on the public open market. Okay, and here is the process. So the banks, they daily publish their inventory to clients, and clients here are hedge funds, which are companies. And typically this use case has 60 clients. Thank you. And what does this inventory include? The inventory includes a list of symbols for stocks like Apple, Microsoft, Google. Then we have the site, whether we want to go long or short. So for this stock, we can assume that long is for buy and short is for sell. And then we have the number of shares that you want to buy or sell, okay, the volume. And as I said earlier, the bank publishes this inventory every day to the clients. The clients look at the list, and if they want to match something, they come back to the bank. They mention what they want to match, and then we execute the trade. So what does this inventory include? The inventory includes the bank's past transactions with clients. And these past transactions can actually reveal some information about future transactions. So let me give you an example. Let's say yesterday we bought from client A a large number of shares. Today we're going to actually add this to our inventory. Doing this action maybe will not make client A feel very comfortable seeing this added to actually the public inventory. since it can leak information. Although the inventory is actually anonymized, it's aggregated, but there's still this leakage. And some clients, indeed, they ask to not add the trades that we do with them in this inventory list. Okay, this leads me to mention what are the current problems with this process. So the current problems are that clients are asking to remove these transactions from the inventory. So we make a reduced inventory available, okay? As I had here earlier, so we are not publishing our full inventory, we have to publish a reduced inventory. And because of that, the discounted prices will not be the same. What am I doing? Okay, that's problem number one. And the client has this dilemma, like, shall I ask to include my past transactions in the inventory and get discounted prices, or like pay like with different prices? And then the other big disadvantage from the bank side is that we are revealing our inventory. Okay, so that's a big leakage. And throughout this process, I was saying that the client doesn't submit anything, okay? So we don't know what the client wants to do. They just see the list and then they can decide. So we get no information from the client. So how we can solve these problems, and what is the ideal solution for these problems? So ideally, we would like the client to send us what they want to do, okay? So let's say here I have an example of an inventory for the client. There's no pointer here, right? Yeah. So if the client submits his intentions encrypted, then we can compute on this encrypted data and try to find matches with the bank's inventory. So here, for example, you can see for the example that I have for Apple, so the client wants to actually sell 100 shares of Apple, and the bank actually wants to buy 800 shares of Apple. So after we compute the match on this encrypted data, the answer is that we can have a match of 100 shares. So you can see that we can subtract the values from the inventory at the end. And how we're going to achieve that solution? So we're going to use secure multi-party computation. I mean, I'm sure that many of you are familiar with it, so I'm not going to stay on this slide. Just to say that secure multi-party computation allows us to compute on private data without revealing any information about the private data apart from the output. And this is what we're going to use here. And the main ingredient that we need to compute in a private way is basically secure comparison. Okay, so back to this example, the main thing that we have to calculate is the minimum between the volumes of the two clients. Okay, we want to calculate the minimum between 100 and 800. And just to mention that we also hide the symbol and the site. And how we do that is that in the US, the number of symbols for this use case is 5,000. So the client submits a list for all of these 5,000 symbols. And if they don't want to actually execute on them, they just put zeros, okay? So this is how we maintain privacy of the symbols and the site for the client. So really, the bottom line is that we need to have a secure comparison protocol for the quantities in the inventory. Okay, so we have two variants. We have the two-party version, the client to bank matching, where the clients come and they submit their encrypted inventory, and then we try to find matches between the bank and the client. Okay, and the benefit here is that now we can actually expose the client to the full inventory of the bank without actually exposing the inventory because we're encrypting everything. And there's no leakage, and only if there's a match, we reveal the information, and then we know what is the match. I mean, it goes public, so you know what was the match, okay? And another thing, so can we do something even more exciting? So we can also do the following thing. I have an example here. So let's say two clients come to match with the inventory of the bank, but we don't have the inventory that the clients are asking, okay? So here, for example, we have 0 shares of Apple. But what we can do, we can actually match the clients together. So we can also offer this client-to-client matching where we can match clients together, and in that case, we significantly increase the inventory that we have available in this system. So think of it as creating like a market, right? And again, I will repeat that there's no leakage here apart from the leakage of finding the matches and executing them. Okay, so I had the example here, so we can have a match of 100 between these two clients. Okay, so for our cryptographic contribution, so we have two-party secure comparison protocol where we have the client and the bank have inventory. Then we have the other case where the bank does not give as input their inventory, and we try to match the clients together. Okay? And the main cryptographic novelty that we have here is that we have a secure comparison protocol, which is actually linear in the sense that we only need linear operations. And that means that we can actually calculate locally because the operations are linear. And we only have 2 rounds for this protocol. And it's important here because you don't want to have a lot of rounds back and forth. Improving the previous works, which required nonlinear operations, so then they are more expensive, and also they had a more number of rounds. So let me go back to the challenges now. So there were many challenges, so I tried to give you one big advantage and one big disadvantage to try to put such a thing in production. So back in 2019, so that's when I also joined the firm. So we are cryptographers, we do secure multi-party computation, so we wanted to see if like the bank wants to put in production such auctions, okay? So the big disadvantage, okay, is that there was no other financial institution using secure multi-party computation. So you go and talk to them, show me an example. There's no example. So that was a very big barrier at the beginning. And again, there were more challenges. I'm just highlighting here the important ones. However, the bank, they like innovation, so they listen, so there was a long process. And so that was the biggest disadvantage. So what is the advantage now on the client side? So again, same situation with the clients. These clients are hedge funds, as I was saying, they never saw secure multi-party computation before. They don't know what this is. And having their data going outside of their company, even if it's encrypted, is it's a foreign thing to them. But the positive thing here is that, again, the bank has very long-term clients, and they were willing to listen and see what we have to offer. Okay, so I can abstract here the biggest challenges. So let me first tell you some challenges throughout the process. To actually first get the internal buy-in to the product. So some steps that we had to do, we had to actually find the right people in the bank to talk about that, which is the quantitative researcher team. And then try to find the suitable use case, okay? So they have a lot of products there, so you have to discuss with them what makes more sense. And that's why we decided on this use case. And then we had to design and show them the first demo to show them that it can be feasible. But the story is not over here, okay? So this is the beginning of the story, and that already took a lot of time to achieve. Okay, so then for the external buy. So the bank will not build something if they don't ask the clients. So another step through this process was to go and ask the clients about it, if they want to use it, under what conditions they want to use it. So we visited almost 20 hedge funds, we were showing the demo, and asking questions about what is secure multi-party computation. So as I said, they were not exposed to this type of techniques. And then the other things that we want to have from the bank is to ask them under what conditions they want to use this product, okay? So, and there was a lot of client feedback. I don't have time to talk about the client feedback. It's yet another talk, who was positive, who was negative. But after, again, a very long process, the bank decided, based on the client feedback, the bank decided to give the resources to build such a tool. And then I'm going to mention only the requirements that we had for the product, okay? So, and these are very important because these are some lessons that we can learn when we want to put such a system in production. So the first one is that the clients, they don't want to talk to other clients. In fact, they want to keep their identity hidden from the other clients, okay? And that requires only talking to the bank. And moreover, having connections between the clients. Okay, to be honest, this is not realistic, okay? When we talk about secure computation in production, we should not actually talk so easily about establishing connections across all of these parties, okay? So we really had to consider a star topology where everybody talks to the bank, okay? And then the clients don't want to install anything, okay? So then we had to actually find solutions to make them use the products. So we had to come up with a web-based solution. Then another thing is that because it's a web-based application, it runs on the client's browsers, it should not be computationally very intensive. Okay? And then, in MPC, we have this concept of pre-processing the data. We cannot use them here because the clients don't know when they will come. We have all these different times for the auctions. They're not even sure if they will participate in the auction some seconds before, so we cannot really use any pre-processing. And then they don't want only semi-honest security, okay? We don't want the clients to start cheating, so we want malicious security. And also, like, some of them, I mean, most of them, they cannot like review themselves, so they wanted reviews from experts and all of these processes, okay? So these were the highlight of the requirements. There were more requirements, okay? And the other thing is frequent auctions, in the sense that you cannot like run the auction and wait forever. So you want also to be fast, okay? So here is the architecture of the system. I cannot point, but essentially what happens, the clients connect to the browser, and then we have this JP Morgan portal, the markets portal, where they connect there to the Primatch UI, which is actually on the cloud. And then on the left side, we have actually this trading platform where we actually have our Primatch server, which is the bank in the previous examples that I was talking about. And these were systems that they were already existing in the bank, so we had to integrate all our code here, and there were yet another like set of challenges. I'm not gonna mention them, but there were a lot, okay? And then our team, it was very diverse. Like we had like from like programmers for different types of skill sets. We had quants, we had legal, cybersecurity, and a lot of different set of people. So I want to extend my thanks to more people than the ones that you saw on the first slide. So now I'm gonna talk super quickly about the cryptographic solutions, and then I'll show you the demo. How much time do I have? That was what? 4?
4 minutes or so.
Okay.
We're a little bit behind, but we want to see the demo.
Yes, okay. So super quickly for the cryptographic contributions. So I'm hiding a lot of details here. I just want to give you only like the super high level idea here. So the main thing to remember is that our comparison protocol is linear, so the parties can run computations locally. So, and how we add privacy, so the parties secrets share their input with the other client. Okay, so we have inputs A and B. So A and B are the two things that we want to compute the minimum. Think that it's their volumes. Okay, so we send one share to the other party, we keep one share, and we run our minimum protocol that computes the minimum between the two values. Okay, and then the bank learns the answer. So we run our protocol actually 3 times. Okay, so one time on the secret shared values, and now we want to check if the clients run the right code. Okay, so we want to add now malicious security. So how are we going to do that? We're going to actually use commitments. Okay, and essentially we're going to run the code that's not the code, like the code with the input that one party is supposed to run to check in the other party. So basically, in the second instantiation, so in the first one I sent you one share. In the second instantiation, I send you a commitment of my other share. So you can run the same protocol on the committed values. And then we have a third instantiation, again, of the minimum protocol, where we actually are using the openings of the commitment to check that the first invocation on the secret shares was correct, okay? That's how much I can say about the technique, since there's no time. If you're more interested, you can look at the paper or ask me. So let's see the demo. Okay, so this is the JP Morgan portal. So I'm gonna show you the client side, okay? So what the client sees when they interact with the system. So here you can see the different auctions that we have, and they run every 10 minutes. So you can see that when the registration opens, so there's a time window when the clients can come and submit their orders. We give here a window of 5 minutes, and then after 5 minutes, we start the matching, okay? So I'm gonna show you the first run. Okay, so here is what they see. So you can see there's the timeline at the top. Sorry, I'm thinking that there's a clicker here. And the client is asked to actually submit their file of the trades to be encrypted. So I have a video here. I don't know how to make the video run with the clicker. Can I click somewhere? No. Can you click? Ah, okay, it's on. Okay, so I have an example here where the client finds an Excel file. Actually, that was me, not the client. And now we upload the file. And actually what the Excel file contains is actually a symbol. I imported like fake symbols here to show you. And then we have the direction, long or short, and we have two quantities, the minimum and the maximum. I'll talk about this in a bit. And here you can see that they are loaded on the browser of the client. Again, I'm showing you the client side, so everything happens locally on the browser of the client. And then in the next one, I think, can you click? So in the next one, we're gonna press this register button, and now everything is registered and sent to the bank server. And we can see here on the top, you can see how many symbols are there and if they're recognized. Okay, so everything is registered. So the middle columns are different. So you need to make sure that the symbol is correct. There are many different systems for writing the symbols, and we want to check that this is what's happening. We want to make sure that the symbol is the right one in the right system. And then the direction is long and short. And actually, we ask the client to submit a minimum quantity so that we cannot match them above this quantity and a maximum quantity. And that's why you see the threshold quantity and the full quantity. Okay, so everything is registered. And then in the next one, sorry, we didn't, so that it would be like that. So here you can see the matching. So the matching time has started at the top, and you saw gradually how it was matching. So first, we matched the minimum quantities of the client. That's why you saw how it was going like that. And then we have the full quantities. So here you can see what is like the final view of the client. So you can see we have like full matches and partial match. So partial match is that you see in the second row, for example, the client asked for his maximum quantity was 440, but we only gave him 300. Okay, so that's why we say they're partial match. Okay, so this is the demo. So to conclude, so we identified the real world use case for MPC. I'm going to go quickly here. And it's running live, and there were actually many challenges, which unfortunately I don't have time to talk about all of them. And I guess for future work, I'll skip that to see if there's any question. Thank you.
All right, one question. Does anybody have anything lined up? If not, we can hop on to the next speaker.
Thank you for your talk. I was wondering how you will deal with the price, the underlying price of the share. And would you be able to do something like that while considering different prices for bidders and for askers? Yeah. And then, I don't know, maybe do something for a whole book order? Or,
yeah, actually, that was part of one of my open problems. So the price in this use case is fixed, okay? Yes. So there's no price. So there's the other concept of dark pools where you submit also like your symbol, your site, your volume, and the price that you want, okay? And this is the setting of dark pools. Actually, we have also a lot of work on that, and also Nigel has a lot of work on that. So this is another thing to consider so that you make it more complex. It's another use case where you can also add the price element. And then you will have also to compare the prices to see if we can get a match. So the situation is that currently to run a dark pool in production, again in the star network topology, the running times that they require from the business, it's like thousands of matches per second, and we are not there yet. So there's a lot of research to be done to reach the running times that they're willing to accept there. Thank you.
Okay, thanks again. Another round of applause for Antigone as the next speakers come up. Okay, this is the final talk of the session, although we will have another session right after this session. So FHE and MPC, this is the final talk. We're going to hear from Eric and Ben about IPA, which is not the beer. All right, so please welcome Eric Tabanek and Ben Savage.
Hello. Are our mics working? All right, I'm Eric. I'm a research scientist at Meta.
And I'm Ben, a software engineer at Meta. And we're here today to talk about interoperable private attribution, or IPA as we've come to call it, a possible new private measurement web standard proposed in the W3C.
Ben and I are super happy to be here today, but like many projects, this is a team effort. So thank you to everyone involved here today and back at home. So the web is changing. Most notably, third-party cookies are going or gone. This is part of a larger effort to make the web private by default for people. This is causing turbulence in digital advertising, breaking ad targeting and measurement. And while both are important, we found measurement was more easily addressable through cryptographic solutions, which became our IPA proposal. IPA is an aggregated measurement system that aims to conform to the new target privacy model for the web. Specifically, our system is designed to only reveal aggregate information about people and for their cross-site browsing history to remain private, even in the face of malicious adversaries. One design choice we made to achieve this goal is the use of differential privacy, which is a useful tool in preventing differencing attacks that can arise from aggregate statistics. We also avoid relying on untrusted third parties. If there's any single party that could be the cause of failure, the risk of just corrupting, an adversary corrupting them is too high.
Our API is also designed to provide utility to web developers, particularly those that use advertising to support access to their content. So let's start with a motivating example. While you're browsing a news site, you might see an ad for sunglasses. Later, you might purchase sunglasses from the retailer's website. And these types of events are happening constantly. So in the past, each individual's journey could be stored in a database. And these events could be joined together using a third-party cookie. Such a database powered measurement statistics such as conversion rate, cost per conversion, and return on ad spend. So with IPA, our goal is for all those individual journeys and identifiers to remain oblivious to all parties involved, but simultaneously we want to continue enabling the computation of these aggregate statistics.
Much of our design was inspired by Prio, which includes an MPC that's operated by semi-trusted helper parties. Now, such a system can't exist on rainbows and goodwill, so we must also consider the business model that will support it. We needed to design a system such that the cost of operating it is borne by those that benefit from it, rather than the browsers. To achieve this, we proposed the concept of a helper party network that consists of distinct entities who are trusted to not collude. We envision an ecosystem of many helper party networks with competition to drive efficient performance and pricing. This ecosystem could be governed similar to the CA Browser Forum, the body that vets certificate authorities.
Now that we've covered our goals and constraints, let's dive deeper into the design of IPA. We propose adding just two APIs to the web platform, set match key and get encrypted match key. Our goal is to link ad impressions and conversions that are associated with the same person. And people often use more than one device. So one idea that we have is to allow sites that people log into across multiple devices to call this set match key API in order to set the same identifier across all the devices that are owned by that person. We would call sites that do this match key providers. But protecting against a malicious match key provider is currently one of our open research problems that we're going to talk about later. So while we're continuing this research, we can fall back on a simpler design that doesn't support cross-device matching by having each device simply generate a random local key. So the actual raw value of this match key would never be revealed to any site. Instead, sites would just call this second API, this get encrypted match key, to obtain a unique, random secret sharing of the match key, where each share has been encrypted towards one of the helper parties in a helper party network.
Let's walk through our sunglasses example again. and see how this works. First, a person visits the website of a match key provider. They log in, and the site sets the match key on the device. Next, the person visits news.example and sees some ads, including our sunglasses ads. We call sites like news.example source sites. At any point, a source site can request an encrypted match key and store it alongside information like the campaign IDs and timestamps of the ads that they showed to that person, including our sunglasses ad. Finally, the person visits sunglasses.example, which we call a trigger site. Again, at any point, the site can request an encrypted match key and store it along inside information about conversions, such as purchase values and timestamps. Get encrypted match key uses a new secret sharing of the match key for distinct sites, preventing sites or an individual helper party from linking reports outside of the MPC.
Next, both sites will send the information that they've logged to what we call a report collector, who is compiling this information into reports that include the encrypted match keys, as well as secret shares of the other data that we talked about, like campaign IDs and purchase values. So the report collector could be one of the two sites that we've listed, or it could be some measurement company to which they've delegated this responsibility. Next, the report collector sends each of the sets of shares to the 3 helper parties that would run our MPC. Each helper party will only be able to decrypt 2 of the 3 shares of the encrypted match key. In IPA, we use a 3-party honest majority network, but other sizes and configurations could exist. Critically, our protocol is designed to be secure, even in the case that one of the helper parties becomes actively malicious.
Now that we've covered how the input data is generated, let's talk about how we produce aggregate measurement results in MPC. So let's first by explaining our ideal functionality before we get into the protocol. A measurement query consists of a set of source reports, these are the ad impressions, and trigger reports, these are the conversions. We first group them by the associated person and sort by timestamp. Then, for each of the trigger reports, we look backwards to see if there's a source event from the same person that preceded it. We call this last touch attribution. Values from the trigger reports are assigned to the attributed source report's campaign breakdown key, which we can view as a histogram contribution. In order to provide our differential privacy guarantees, we need to ensure that the total contribution from each person is capped. Here we're showing an example where it's capped at 10. We collect all the histogram contributions in the query. We then generate random noise according to our differential privacy parameters. Finally, we aggregate all the histograms, including the random noise, and release the differentially private outputs.
Now let's talk about how we were able to implement this functionality in MPC. So as we mentioned earlier, we're proposing that a helper party network consisting of 3 independent parties operates a 2 out of 3 honest majority MPC. So we arrived at this security model as it represents a reasonable trade-off between the real-world security considerations and performance. Notably, we've been able to leverage replicated secret sharing, which provides really efficient multiplication, as well as malicious security compiler that results in only approximately a doubling of the cost over a semi-honest protocol. Here's some of the papers that we've used.
Peeking ahead, we're going to need to sort by this match key to get all of a person's events grouped together. To accomplish that, we want a bit decomposed representation of the match key, with each bit shared in a large prime field. This introduces a real-world trade-off. Bit decomposition in MPC is expensive, and it would actually be really easy to have the browser generate a share for each bit. However, this increases the client communication by at least an order of magnitude, so instead we send them in Z2.
From here, we use a modulus conversion protocol that's based on work by Kikuchi et al. That keeps our wire format compact and avoids the sort of expensive bit decomposition. Now, we're able to perform our sorting. Our goal is for all the reports that have the same underlying match key to be adjacent to one another and sorted by time. So naively, you could accomplish this via an oblivious sort by both match key and timestamp.
We realized that the timestamp doesn't need to remain oblivious, at least to the report collector, and thus they're able to pre-sort by timestamp before the MPC. We can then use a stable sorting protocol to sort by the match key, and the reports will be grouped together by match key and in chronological order, just as we need them.
We considered a few different sorting algorithms with a special focus on communication efficiency, because egress from data centers is likely to be the biggest driver of the dollar-based cost of our system in the malicious setting. So in that case, radix sort wins. Continuing with communication efficiency, we found that sorting by 3 bits at a time is the most optimal. Our current implementation using radix sort is from this efficient, secure 3-party sorting paper by Asherov et al.
With our reports sorted, we're on to our last touch, attribution and aggregation. For the most part, this is a fairly generic MPC, so we won't spend too much time going through each step of the protocol. But instead, we'll continue to focus on the interesting decision points.
One issue that isn't well supported by generic techniques is the need to look back at several preceding rows. For example, if a trigger report was not immediately preceded by a source report, but had other reports in between. So GraphSC offers an interesting solution for these types of lookbacks with O of n log n communication. It works by comparing first to the row 1, and then 2, and then 4, and the powers of 2 above. In order to achieve differential privacy on our outputs, like Eric mentioned, we need to make sure that each person's total contribution to the output is capped. So we leveraged more ideas from GraphSC to sort of scan through every individual person's contributions and add them up. Then we use this range check protocol to get the sum of these contributions and contain them, using this work from Nishide and Ota.
The final step is to aggregate contributions and release DP outputs. The simplest approach to generate this noise is to have each helper party generate 1/3 of the random noise independently. But we're exploring if it makes sense to do this in MPC. Exactly how much noise is added is the subject of both research and standards conversations. We also need to ensure privacy across queries, not just on individual queries. To achieve this, we're proposing that individual sites will have a privacy budget of epsilon over a given epoch, likely a week. Each query will include a query-specific epsilon, which must be less than or equal to their remaining budget. Helper parties will keep track of that budget and reject queries once it's exhausted. Note that this design only limits the rate at which sites gain information about users. But in infinite time, the total amount of information is unbounded. We believe this to be an acceptable trade-off, as only sites that have long-term relationship with users are able to obtain additional information in this way.
Now that we've covered IPA as it stands today, we'd like to present a few open areas of research. In order to support the largest publishers, this protocol is going to have to scale to support billions, possibly hundreds of billions of reports in an individual query. So this will almost certainly require some form of sharding. And this is really tricky, as all of the users' reports have to go to the same machine, and thus a shard size could potentially reveal information about which users end up on which shards, and possibly even which users are in the intersection of source and trigger events. This is further complicated by the fact that we aim to keep these reports in chronological order to save computation on the sorting. So we're currently working on ideas for oblivious, stable sharding with differentially private shard sizes.
Our privacy budgeting system is very simple, potentially overly so. Every query that a report collector makes deducts from their budget for the given epoch. This is even true for 2 queries with absolutely no overlap in people. However, by design, it's impossible for a report collector to know if, or for any individual helper party to know if 2 queries have overlapping people. Additionally, report collectors need to be able to be aware of how much of their budget remains to properly manage it. We haven't been able to make any real improvements to this simple design, but it could be an area where novel research may unlock much more efficient budget usage.
And the last area of research that we're going to highlight is the privacy story associated with the match key provider. Like I mentioned earlier, we recently found an attack that allows a malicious match key provider to collude with source and helper sites to exceed their privacy budget. So as a fallback, devices can just generate a random match key value. But we're actively researching new approaches to match key providers that could both enable for cross-device attribution and conform to our target privacy threat model. Even without cross-device attribution, we think that IPA provides unique value compared to other related proposals.
To better understand that unique value, let's compare IPA to two other private measurement proposals most discussed in the W3C's Private Advertising Technology Community Group. So the aggregate attribution reporting API, ARA, is part of Google's Privacy Sandbox, and Apple's private click measurement is currently deployed in Safari.
The first design dimension is the use of some kind of server component that performs a private computation. So whereas IPA and ARA both rely on some kind of server-based private computation, PCM does not. As we'll see, that has a lot of implications. IPA proposes the use of an MPC, which we just described, whereas ARA proposes the use of a TEE, hosted by some cloud TEE provider. But in principle, either proposal could theoretically be implemented in either of these setups. Next is the privacy definition. So both IPA and ARA propose the use of central differential privacy. PCM, on the other hand, is purely information theoretic, relying on just limited entropy in the reports and the pigeonhole principle to assure that most, if not all, reports contribute to some kind of cohort. This does provide the ability to perfectly track a limited number of people at the expense of broader measurement capabilities.
IPA allows the report collector to specify many values, like the breakdown keys at query time, but ARA and PCM handle this problem differently. Instead, sites call the APIs to register an impression or a conversion when they happen, and then they are attributed on the device. Information like the breakdown keys and the purchase values have to be provided to the API when it is called. As a result, IPA provides much more flexibility in the measurement capabilities. Because ARA and PCM perform the attribution on device, they require a random delay to disassociate the call to the API from the output of the API. These delays, in turn, impede the ability for sites to understand performance and sometimes even result in dropping reports, hurting overall utility. IPA mostly avoids this, as calling get encrypted match key immediately returns an encrypted match key. That said, sites do have to wait to collect enough events to produce meaningful aggregates.
In the worst case scenario, that the security properties of the entire protocol fail, either through exploit or error or helper party collusion, IPA would leak all individuals' data in the system. ARA, in such a scenario, would also reveal individuals' data, though less so than IPA because only information about people who both saw an ad and made a purchase would be released. PCM doesn't rely on a private computation environment, so this is a little bit different there. Cost is correlated with complexity, but complexity also has implications on understandability. PCM is essentially free, so in comparison, both IPA and ARA are expensive, though both are still a small fraction of the relative advertising costs. As currently planned, ARA would deploy on TEEs, which would likely be cheaper than MPC. The cryptography and differential privacy that's used in both ARA and IPA makes explaining them to end users non-trivial. PCM sort of avoids server-side computation and differential privacy, which makes it easy to explain functionally how it works to users. Ironically, this makes its privacy definition, at least academically, quite weak.
I'd like to leave you with a parting thought. Advertising is an important financial tool for providing no or low-cost access to sites on the open web. The work happening by all the folks in this room is pushing humanity closer to the ability to operate at the efficient frontier between privacy and utility, where privacy does not have to come at the cost of all utility. With some hard work and some real-world crypto, I fundamentally believe the ad-supported business model can be rebuilt in a way that conforms to the target privacy model of the web.
We invite you to join our efforts to make the web more private. This QR code links to our proposal, including links to all the ways in which you can help us out with our efforts, such as there is a draft of an academic paper that would benefit from feedback. There's our code base, where we've implemented this in Rust, and if you want to test that out or review our implementation, we'd appreciate that. There's also issues for all these open problems that we mentioned, and there's information about a bi-weekly call, where we work through these issues and more. Finally, the incubation of this and related APIs is happening in the W3C through the Private Advertising Technology Community Group, or the PATCG. And this group is a community group, so it's open to anyone, and we invite you to join.
Thank you.
Thanks.
All right, well, that's definitely more complicated than third-party cookies. Okay, well, thanks, folks. I think if we don't have questions, we'll move on to the final session of the day. So I'd like to invite Stanislav